Hello, I'm back with a new series of videos based on the previous videos that I've worked on regarding the fixed voltage regulator that I built. This time we're going to start a new series based on that, and this is going to be building a power supply, a variable power supply from 0 to 15 volts at a considerable amount of output current, which I haven't determined at the moment, but the voltage output will be from 0 to 15 volts. And this will be based on that last video. If you checked last video, we built this circuit that's shown on the screen, and I modified this circuit to provide, first of all, a better constant current into the Zener reference here, so that our output won't fluctuate, which is basically giving us a constant voltage on the output at all voltages from 0 to 15 volts. And also I'll be adding a mode of constant current operation using this resistor here. It's shown here with 5 ohms right now, but will be considerably smaller, and we'll use that shunt resistor to sense the output current on the high side of the output transistor here. Okay, the modified circuit is right here. So hopefully you can see this modified resistor. The first modification that I included is to give it better stability in terms of regular constant current into our main reference Zener here, and I'm using a special circuit arrangement called the cascode. It's basically cascading 2 transistors in series like this to give you a better stable voltage control at this point here. And if you remember from our last circuit, we introduced this current source here. But this current source fluctuates. The voltage here fluctuates. The voltage at this point fluctuates due to temperature variations and of temperature dependence of VBE here will produce a fluctuation of current here. So this cascode circuit here is meant to fix that. And also there's a term called early voltage that affects this arrangement here, this current source here. That early, if you want, you can read about it. There's so many articles written about it. It's called early voltage, and that affects the voltage at this point here, which in turn affects the current stability of this current source. So to eliminate that, I've introduced this cascode circuit here. So the way it eliminates that variation here is by fixing this collector voltage here. This collector voltage is fixed by this voltage here. Since this voltage here is constant here, whenever this voltage changes at the input here, this voltage will be relatively constant, and that will be this voltage will be constant. Thereby, this collector voltage will be constant of this transistor, and the variations due to early voltage will be eliminated here, and also due to some of the temperature dependence of VB of this transistor will also be eliminated by this circuit. If you want to calculate what values to set your resistors here, all you have to do is determine how much current you need on your on this resistor here, which feeds your Zener reference here. And for my case, from the data sheet of this Zener that I'm using, it's a 6.9 volt Zener. 6.9 volt is regulated when you apply a 10 milliamps of current through the Zener. Therefore, my current in here should be about 10 milliamps. And then basically what you do is you select a resistor here. So for my case, I just selected three 1K resistors in parallel to give me 333 ohms. And if I want to get a current of 10 milliamps, I need a voltage of at least, so we get 10 milliamps multiplied by that would be 3.3 volts across here, right? Yeah. So for my case, based on the tolerance of the resistors and everything, happen to have 3.71 volts, and that gives me around 11 milliamps of current flowing through here. To achieve that 3.71 volts across here, which gives me 17.4 with respect to ground at this point, I'm gonna go so basically if we go back, I'm gonna go by 0.7 volts down here, which is gonna give me 20 minus 4.4, that is 16.6 volts around here. So to get that 16.6 volts, I've used 1, 2, 3, 4 silicon diodes here for a total drop of about 2.6 volts, and a green LED of 1.89 volts, so about 1.9. All in all, giving me 4.4 volts drop here. So that fixes my voltage here. So all I have to do now is to fix this voltage here. And so basically this is 16.6 volts. Hopefully that's visible. So that's 16.6. Then basically, if you set a current to go through here, you can arbitrarily, select a, high enough current here, such that the current that passes through here is at least 10 times smaller than this. So if you do that, you come with 7K and 6.6K here. And that will fix your voltage at this point here to 9 volts, basically. So 9 volts, you go 0.7 again. So this will be 8.3 volts here to ground, basically. So 8.3 divided by 6.6 kilo ohms. If we do that really quick, 6.6 divided by 8.3 divided by 6.6K. So about 1.3 milliamps of current. So around 1.3 milliamps of current. So if I go to my circuit here and measure that node here, so if I measure this node here right at this point, sorry, this thing is not focusing. So if I measure that voltage with respect to ground, so you can see here, and that resistor is right here. So there you go, it's 8.31 volts. So yeah, that should be enough current to fix, should be more than enough current, at least 10 times bigger than this current that goes into the base of this transistor to keep it in its linear mode of operation. And basically this is 6.9, so when it's happy, it's getting its 11 milliamps of current, which I can show you here, which is this change it to from AC. So you can see that it's measuring 11 milliamps of current, and that's hooked up to here. There's my Zener reference. But okay, moving on and describing the rest of the circuit, because we want to finish this really quick. And as usual, I put 2 microfarad capacitor here to smooth any variations in voltage here due to noise or anything. So I put 2 microfarad. So I use a special op amp, LM358, and I've changed it from the previous op amp that we used. We used TL082. And I'll tell you the reason why I chose LM358 in a minute. But I use that, and since this is 6.9 and we want it on our output here about 15 volts. So what I'll do is I'll use a non-inverting amplifier configuration to boost my voltage here from 6.9 to a manageable size here, higher than what my output was should be, because I will be buffering it through the transistor. Remember, the transistor will have a drop here, right? So we need to have a higher voltage here, which will feed through this variable resistor here, which will control our variable voltage, to vary our voltage on the output. So we need a higher voltage. So for my application, I chose this voltage at the input here to be around 6.6 volts. So in order to get that, I need a gain of about 2.33, and if you do the calculation, 16.6 divided by 6.9, which is my Zener input, right? And I need 16.6 here. So yeah, it's about 2.4. For my application, it came 2.33. The two resistors I selected, they give me if you do the calculation for the non-inverting gain, the voltage gain AV is, we know that here I'll use a separate paper here to calculate that. 1 plus my two resistors are 36 and 27. 36 on the feedback, 27. This is the gain, and that comes out to be 36 divided by 27, and that gives you that, and then plus 1. There you go, 2.33. So that is the voltage that I get on the other side of the op-amp, on the first stage of the op-amp, and 2.33 multiplied by 6.9 gives me around 16 volts. More than enough. It's higher than the 15 volts output that we need on the output here. Yeah, so that will be here, and I'm dropping it to ground through a 100k resistor. So the current requirement from this is very, very minimal, right? So it doesn't matter. And that is buffered to control the transistor through the second LM358. I'm using the 8-pin device, so it has two LM358s inside it, 2 op amps, and the second one is basically used as a buffer, almost like as a buffer with a gain of almost 1, because I'm using 10 ohms with 56k to get the feedback, and it's negligible. Basically, this won't give you any it will, but it's very, very tiny. So and I'm using that basically to it's sort of like a discharge when this is disconnected, when the load is disconnected. The cap here, the output filter here, won't remain charged. It will just discharge through this path here, so that's why I have this here. So sorry. And yeah, so basically that's it. And I'm using, as normal, the a series pass transistor here. So this series pass transistor through a negative feedback will be adjusted. It's shall we call it, quote unquote, its resistance will be adjusted based on the setting of this resistor here. And this shunt resistor right now, I have 5 ohms on it, and I'm just using it for current limiting in case the output gets shorted, right? Because if the output gets shorted, this voltage is going to dip to 0, and this op-amp is going to try to turn on the transistor hard, like fully, which means it's going to pull tons amount of current from here, from my power supply over there. So it's gonna pull all that current to ground. So this will limit the maximum amount of current that can pass in case when I'm playing around, if I short this output. Yeah, but for the next session, when we introduce a constant current operation into the power supply, this shunt resistor will be used, and it will be a lot smaller, and it will help us to design the current control part of the circuit. Yeah. So just giving you a full overview of the circuit right here. As usual, my input filter. This could be fed from, well, right now for testing purposes I'm feeding it from a power supply. But once we have completed the constant voltage, which we are doing right now, and the constant current part of the circuit, the control circuit of the part of the circuit, will introduce a full wave rectifier here and a mains transformer, and this will be a complete linear power supply that you can use in your lab. Very stable, very clean output, DC output basically. All right, so let's go and see the operation of the circuit. So I'm just gonna quickly clean this up. Oh yeah, and my bad, I forgot to mention the reason why I'm using LM358. I want my output to go from 0 to 15 volts, right? So if I used the other op-amp that I used on my previous video, TL082, you cannot input a 0 volt here at the input of this op-amp, because the common mode input dictates that this should be at least 1.5 volts above ground, or no, 1.5 volts below the top rail, the positive rail, and 1.5 above the negative rail. So the common mode range of these two inputs is limited, so you cannot approach the supply rails. But LM358 is especially designed such that the two inputs here, they both can be driven to ground, so you can put right. It's because it's optimized for a single supply operation. These two inputs can be driven all the way to ground, which means we won't have any issues with that. If the common mode range includes ground, basically, if you want to put it into a technical term. And if you see its data sheet here, this is the data sheet for the op-amp that I'm using. So it says here, input common mode range. The minimum you can input into the two pins is the positive or the negative input of that op-amp is 0. So it's perfect for our operation, because if we put 0 volts here, by virtue of negative feedback, this will be 0, this will be 0, this will be 0, and this will be 0. So this transistor will completely shut off, and our output will go to 0. So it's perfect. So we can go all the way down to 0, because if you're aware, some commercial voltage regulators like the LM317, you cannot, like, their outputs cannot go to 0. The outputs can go only to 1.25 volts in case of the LM317, for example. But for our case, this discrete control voltage circuit part of the circuit will allow us to output 0 volts, which is what you require in a properly designed DC power supply. So that is a good a good design that we're using here to make voltage from 0 to 15 volts. All right, now that I have described that, let's continue to the demonstration of the circuit. So I'll just refer to this circuit and show you the setup here. So there is the I have set it up in a breadboard here, so hopefully this will be very visible. So I'll describe it from the input. This is the input filter cap, the 1000 microfarad, and the input voltage is right here. I'm getting it from my power supply here, and currently I'm inputting about 21.4 volts into the circuit, which is basically here. By the way, I forgot to mention that this circuit can operate 18 to 30 volts, and I'll quickly describe why that's the case. Since we are trying to regulate about 15 volts, for this case, when everything was designed, the maximum output voltage is about 16.4 volts, which I'm outputting right now. So if you take a look here, this meter here is measuring my output voltage. It's 16.4. So you need a minimum input of 18 volts here in order for us to regulate that maximum voltage 16.4, we need an 18 volts, and that has to that's also affected by this resistor here, because I'm using 5 ohms now, but we can lower it, and which allows us to get close to the, and you know that when this transistor fully saturates, when this thing turns on like fully, the drop from here to here will be, if we see the spec, usually it's about 0.2 volts, but since this is a power transistor, it's going to be a little higher than that, around maybe 1 volt or so, because it's a power transistor that I'm using. So when this fully saturates, there will be at least 1 volt drop. So that will be dictated, that will dictate how much voltage we can input on this side here. Yeah, and since I'm using at here about 16.3 volts here to regulate that as my input into my buffer here, where I can, you know, get any part of 0 to 16.3 volts. I'm sorry. I've had cold recently, so please pardon me. Basically, what I'm saying is, because this will be 16 volts, we cannot. So basically, this is 16 to minimum will be when, if this has to be 18 volt, this has to be 18 volts or more, because when this op amp outputs 16 volts, this, you know, on the output of this LM358, if we go back to the data sheet, the output swing of that op amp, the output swing, say for example an input voltage of 30 volts with a 10 kilo ohm of it can output only 27 volts, right? So there is a drop from the positive supply to the output, right? So so because of that, we have to give it some margin. So this has to be higher than from the voltage that we are regulating on the output. So minimum 18 volts input. Maximum is 30 volts. The reason is dictated also by the op amp, since the op amp is also powered from this rail here to ground, and the op amp can only tolerate plus or minus 15 volts, so a total of 30 volts on the input here. So that's our maximum we can input here. So okay, so those are the limits that we have to follow. All right, so to the operation of the circuit here. So as you can see, there's my LED. There's the 4 silicon diodes that I'm using to these silicon diodes here to lower that voltage to here from 20 volts. This is some filter caps here around, you know, around this area to quiet it down. There's that filter cap here, and I have another filter cap. Where is this filter cup hooked up to? Yeah, sorry, those are the 2 decoupling cups. These 2 are decoupling cups for the op amp. I'm not showing them, but these are decoupling cups to ground. Right? Okay. So that's a decoupling cup. This big one there. Yeah. Okay. And this is the power transistor, which is used to, you know, used as a quote-unquote variable resistor to regulate the output. There's my 100k resistor that I use to adjust the output of the voltage. There's my load. My load is about 1.4k. So right now, when it's fully turned on, like to its maximum voltage of 16.4, I have 11.3 milliamps of load. But I will I will load that significantly once I demonstrate the yeah. Okay, so let's demonstrate the variable output voltage right now. I'm gonna use here this screwdriver. I'm gonna use this screwdriver to vary the voltage. So if you take a look here, the bottom meter, so I'm gonna lower down the voltage, as you can see. the voltage is going down, and I'm going to vary it all the way. So if you see, this is what I'm doing. I'm so basically adjusting the voltage, so you can see it's getting adjusted from the maximum output down.